ओके, नमस्ते एन्ड गुड इभिनिङ टु अल। म हरिशङ्कर मल्लिक। आजको यस एनपीएस मन्थली टक सिरिज अन्तर्गत चौथो टकमा सम्पूर्ण उपस्थित महानुभावहरूलाई मेरो व्यक्तिगत तथा नेपाल भौतिक विज्ञान समाजको तर्फबाट स्वागत गर्दछु। यस कार्यक्रमको सभापतित्व गरिदिनु हुन यस समाजका अध्यक्ष प्राडा नीलम श्रेष्ठ प्रधानज्यूलाई हार्दिक अनुरोध गर्न चाहन्छु।
नमस्ते एन्ड वेलकम मिम लाल सर।
आजको यस टक प्रोग्राममा स्पिकरको रूपमा यस समाजका आजीवन सदस्य तथा उदयमान भौतिक शास्त्री प्राडा मिम लाल नकर्मीज्यूलाई हार्दिक आमन्त्रण गरेका छौँ। हाम्रो निमन्त्रणालाई सहर्ष स्वीकारी यस कार्यक्रमको शोभा बढाइदिनु भएकोमा प्राडा मिम लाल नकर्मीज्यूलाई हार्दिक धन्यवाद भन्न चाहन्छु। साथै उहाँको छोटो परिचय राखिदिन हुन यस समाजका कोषाध्यक्ष डाक्टर हरिकृष्ण नेपानेज्यूलाई आग्रह गर्छु। हरिकृष्ण।
Thank you, Dr. Harisankar Malik sir. First of all, I'd like to welcome Professor Mim Lal Nakarmi in NPS monthly talk series today. And I'm going to read the short brief CV of our today's speaker, Professor Dr. Mim Lal Nakarmi. He's a professor of Dr. Mim Lal Nakarmi, Department of Physics, Brooklyn College of CUNY. And he has done his PhD in 2005 in Department of Physics, Kansas State University. And his research area, wide bandgap nitride semiconductor. And he has BSc in 1995, Biral University Institute of Technology and Science, Rajasthan, India. And also he has completed his master degree in physics in 1995, Tirban University, Kirtipur, Nepal. And currently is involving in professor of physics in Department of Physics, Brooklyn College, CUNY, New York, since 2021 to present. And he is a coordinator of engineering program at Brooklyn College, Chair of Physics, Brooklyn College, since 2022 to present. And you are 2015 to 2020 in Department of Physics, Brooklyn College, CUNY, New York. And also he was a lecturer, assistant professor since 1994-2000 in Department of Physics, Kathmandu University. And his research area are divided into three categories. First, his research area in interest, optical study of photonic materials, bulk, thin film, nanowire, nanoparticle, multi-quantum wire using the photoluminescence and reflection spectroscopy. And second, study of structural and electronic property using the Hall effect, X-ray diffraction, atomic force microscope, and scanning electron microscope, transition electron microscope, and surface photovoltaic spectroscopy. And third, the synthesis of wide bandgap photonic materials, third nitride, like gallium nitride, aluminum gallium nitride, boron nitride, and their alloy. And second, oxide, like zinc oxide, magnesium oxide, and their alloy. And he has a contribution in education development and he is implementing the active student centered active learning environment in the undergraduate physics in general physics course. And he has prepared and submitted its pattern in title ultraviolet and deep ultraviolet light emitting with unconventional layer design, which is submitted pattern. And he has all total more than 67 published journals, and the Google Scholar Index and citation, yes, citation of his journal 4,711, and H index 32 and I-10 index 44. And he has more than 67 international journal. And I'm reading a very short brief CV of Professor Dr. Mim Lal Nakarmi sir. And thank you, Harisankar Malik sir.
Thank you, Harikrishna Panji. Now it's the time to Mim Lal Nakarmi sir. The floor is yours.
Yes, sir.
देखिन्छ sir.
Okay. Right. Good evening, everyone in Nepal, and it's actually good morning in USA. Right here, it's just morning. And thank you, Nepal Physical Society, for inviting me in this talk. And I'm very glad to share my experience and my work with all of you. And hopefully it will benefit you and me. So today I am going to talk about atomic light emission in UV region from hexagonal boron nitride for quantum emitter. And before I start that talk, I would like to say some of my work and related field and where it will be going towards. So my work is related to, or it has application in the lighting system. And here are some kind of history of our lighting system. It started from oil lamp, or it's even before invention of electricity. So after the invention of electricity, incandescent lamp was developed for our general purpose lighting system. But its efficiency has not increased that much even since its development. So maximum efficiency we can get from incandescent lamp is like 5%. So out of 100 rupees, we spend 95 paisa will be wasted, and only we get a light for 5 paisa. So it's a huge waste of energy. So another little bit higher efficient lamps are fluorescent lamp, and it has better than the incandescent lamp, but still its efficiency could be around 10–15%. And but it is much better than the incandescent lamp. But the problem with this is the efficiency is not still high enough, and it uses the mercury. So it is based on activating mercury, and mercury emits the UV light, and UV light is absorbed by phosphor coated inside that tube, and then we get the white light. So the next generation lamp is LED, light emitting diodes. So these are based on solid state semiconductor diode, and its efficiency is very high, and then it is the 21st century lighting system. So the efficiency could be 40–50%. That means we can use many bulbs instead of one incandescent lamp with the same price. So these are the materials, wide bandgap materials. Those are used for developing those LED lamps. And because of the main player was the gallium nitride. Gallium nitride, once the gallium nitride was realized to develop the blue LED. So before there was red color, green color, and other colors, but blue was not there. So because blue was not there, we cannot make it white. So it has to have a RGB color. So after invention of blue color, we were able to make white color, and that we use for the general purpose lighting system. For the invention of that blue LEDs, these three scientists, all are Japanese, but I think two of them are currently in USA. They received Nobel Prize in Nobel Prize of Physics in 2014. So gallium nitride, these aluminum nitride, indium nitride, zinc oxide, these are the materials called wide bandgap semiconductor. When we say semiconductor, the first material it comes in our mind is the silicon. Silicon has band gap 1.1 eV. And band gap is the most important physical parameter in semiconductor that determines most of its properties and also where this material can be used. So gallium nitride, aluminum nitride, indium nitride, these three groups are all direct band gap material. They have the same structure, Urdjai structure, and band gap can be tuned from 1.9 to 6.2 eV. So it covers from infrared to deep UV spectral range. So that's why it has a big application. And then as we try to increase the band gap, it also gives the challenge for the material growth, having the conductivity. So people who are also working on other material, another candidate for the wide band gap material for this light emitting diode is zinc oxide. And people who work for at least 10 years, 1 decade, and then it still has a problem with p-type conductivity. Now another material scientists are working is boron nitride, hexagonal boron nitride. And that's the one I'm going to discuss a little bit more in detail. And this white light, after the invention of white light, I mean the LEDs, we can make the different color of LEDs, all colors of LEDs, and we can mix it up, make it white or even whatever the color we want. So in future, it's not only we can control the intensity of light, we can also control the color of the light inside the house, and we can feel different. Maybe we can feel like a morning, maybe evening, or in the daylight time. So it all depends on the mixing of color. And these are already in the market. As you might have used the flashlight, LED flashlight, that can last longer because of its efficiency. And in the household, light bulbs are already here. This is the Philips light bulb, and they are already in the market. And some of these light emitting diode based lightings are very efficient and bright that they are already used in the street as a street lamp. And another application is a little bit advanced technology, which is this LD laser diode. So once LEDs can be is manufactured, the higher technology is the laser diode. So these laser diodes, earlier we used to have a CD that can store, I think, something like 700 megabyte, and that uses red laser. And then after that, DVD came, and DVD uses blue laser for the reading and writing. And now there is Blu-rays. Blu-ray uses purple color 405 nanometer, the gallium nitride based laser. Its color is purple, but I don't know why it is called Blu-ray. All right, so my interest is in the ultraviolet light, how to generate the ultraviolet light. So as I said before, if we increase the band gap, we can generate the short wavelength LEDs. And we have to have the corresponding material that matches the band gap. So ultraviolet lamp, if we look at the spectrum of solar spectrum here, solar spectrum is cut off at 280. So below 280, they are all absorbed by ozone. So ozone is actually protecting us before it absorbs it, and before it arrives to Earth, it is absorbed, and there is no UV ultraviolet light signal below 280 nanometer. So because of this, this emission or light emission, if we have in the Earth, that is actually made by man, either made by scientists, or it is generated by some kind of incident or event, and those are normally emitted from missile emission, missile explosion. So this any detector in this range are used to detect missile explosion. So there is also interest in the military purpose. And another reason of our application of these LEDs in this range is, since the biological organism in the Earth did not see the radiation, UV radiation below 280, so they have not developed the immune system in this range. So that's why if we have a lighting system in this range, they can kill bacteria, because bacteria have not developed the immune system in that range. So this is currently this is called the germicidal UVC range light, and they are used in the disinfection or sterilization, or also some water purification by killing bacteria. And because of the pandemic, COVID pandemic, and this is also highly demanding, and scientists are revisiting again to develop this UV LEDs. And another purpose is, as I said, in the general purpose lighting. So how can we use the UV LEDs for the general purpose lighting? Like in the fluorescent lamp has mercury, and mercury emits the light at 253 nanometer, and that light is absorbed by phosphor. So just like that, once we have the UV LED, we can put the fluorescent material, phosphor, on top of that, and then phosphor will absorb the UV, and it re-emits all the color, and that makes the white. And UV also has other application in industry, research, and then medical field. So this is my interest, and the materials I'm working has application in this area. So main interesting point of these LEDs are, these are solid state, and these are small, portable, and it is very efficient. And once it goes for the scale up to the high mass production, it could be cheaper. All right, so a little bit about the semiconductor material. How do we choose the material, and what are the requirements to make the LEDs? So first thing is, as I said, band gap is the most important parameter, and band gap is determined based on its atomic structure and how the material is made from, and what is the bondings. So most of the silicon, like silicon, most of the semiconductors have covalent bond, and it makes the complete octant. So for example, silicon, right? Silicon, 2 silicon makes, it has 4 valency, and 2 silicon makes 8. And if not in the compound semiconductor, let's say if we mix 3rd and the 5th, 3 and 5 makes 8, and 2 and 6 makes 8. So those materials are actually semiconductor materials. And these materials band gaps are different for different material. And that band gap, based on that band gap, we call is some are wide band gap. If the gap is higher than 2.5 or these days higher than 3 eV. So another requirement is the direct band gap semiconductor. In the electronic band structure, the highest field band is the valence band, and another band above the valence band that can have the excited electrons, that's the conduction band. If the top of the valence band and the bottom of the conduction band has the same momentum K, then that's called the direct band gap semiconductor. And if not, if the bottom of the conduction band is at different K values than the top of the valence band, then that is called the indirect semiconductor. So what it has to do with the LEDs. When we have the electron in the conduction band and a hole in the valence band, if it is the direct band gap semiconductor, electron and hole recombine, and this is kind of a collision problem. So it has to conserve energy and momentum. So if the K value is same, then momentum is conserved, and energy is conserved. The difference of the energy is emitted as photon. But if the K values are different, then in order to conserve the momentum, it has to involve another things. So that is normally phonon. So because of the involvement of the phonon actually just gives the heat. So the efficiency is very low in the indirect band gap semiconductor. So that's one of the requirements. And then to make the diode, we have to have one material N type and another material is P type. So N type is the material which has lots of electron, and then P type is the material which has holes. So for the wide band gap semiconductor, because the gap is so wide, we don't get the thermally excited electron in the conduction band, and that is not actually we want. We like to have the control concentration of electron or hole. So that is done by doping. And doping means mixing some small amount of impurities. And if the energy level of the impurity is close to the conduction band, then now the energy difference between the conduction band and that impurity level is small, and that can be excited even with the thermal energy. Then we get the lots of electron, and that material is N type. And similarly for the P type, we also try to find another impurity whose energy is close to valence band. Then that material can absorb electron from valence band. Then we get the hole in the valence band. So that material is P type. And those P type and N type materials are grown in the synthesis of material. They are grown at the same time. For a while we make N type, and right after that we make the P type, and that middle is the junction. So, but the current LED structures are made with quantum well. So for the quantum well, we also put little bit of another material to make a alloy, and which makes the band gap smaller. And when the band gap is small for this small thickness, and then it is the quantum well. It is exactly the same quantum well we study in quantum mechanics, and the energy levels, whatever is, will be same as we calculate in the quantum well, quantum mechanics. So the frequency or the wavelength of the light is determined based on what is the material we use in the quantum well, and then the one side will behave as a cladding and another will be also behave as cladding. So those two cladding confines the electron, and those confined electrons when recombined emits the light, and that's why it is efficient. So what determines the wavelength is the band gap. For a shorter wavelength, we have to have a big energy gap. That's why for the UV, right, UV is short wavelength, then we need to have a wide band gap material. All right, so this is a little bit practical knowledge of some pictures of the real LEDs. So most of the time it's not only the one well. Normally it has multiple quantum wells for higher efficiency, and these wide bandgap materials are grown on mostly on sapphire, and it's not only one N-type and P-type, because there are lots of things to take care when we grow the crystal, because we like to have a high crystalline quality, and then once we grow in the different substrate, we have to manage the stress, otherwise it will make crack, and then the crystal structure could be different. And then there are also many layers which is required, thick layer which is required for the contacts. So in one LED structure, it could have more than 20 different layers. And for the laser diode structure, you will have even many more. So then after that, these materials are etched means it's cut down to the N-type, and also put the contacts on the N-type and the contacts on the P-type. So that is done after the growth is completed, and then those materials are cut into small pieces, and then put the wire bonding, and after that it is encapsulated. So that makes it one LED, and normally one LED structure is about 300 micron by 300 micron. So if we can grow a big wafer, it can be made thousands of LEDs from one wafer. So this is the one deep UV emitted at 280 nanometer when I was a PhD student. So I am still continuing the research on the same field, and I also work a little bit on the zinc oxide, and currently I'm working on this boron nitride, hexagonal boron nitride. So I'm going to discuss a little bit in detail about this boron nitride. One of the phenomena we observed in the boron nitride was atomic-like emission from our photoluminescent system in the UV region. So I'm going to discuss in detail about this. So a little bit about background of boron nitride and our experimental setups and experimental results on boron nitride bulk crystal and powder sample. And also we did some XPS analysis for further investigation of the defect, and I will summarize my talk. All right, so hexagonal boron nitride is recently emerged after the demonstration of leasing action at 215 nanometer by a Japanese group. They grow hexagonal boron nitride crystal, and then they discover that it can be used for the lasing action. Meaning it can be used as an emitter, and its emission was very strong, so it lases. So after that, most people working in a wide bandgap semiconductor started looking at that. And one puzzling was theoretical calculations. It indicated that this material is not a direct bandgap material, but the experimentally it shows it can be lased at 215 nanometer. That means it must be direct bandgap. So after lots of people, even there was some controversy, or some people claim it's a direct bandgap, some people claim no, and then finally, but none of the theoretical calculation says it is a direct bandgap. And finally, it is proved that it is an indirect bandgap semiconductor, and the strong emission is actually because of the photo-assisted emission. So I will discuss it a little bit detail in later. And hexagonal boron nitride is different from gallium nitride, aluminum nitride. Its structure, crystal structure is different. It's a layer hexagonal structure. It is similar to graphene. So graphene is made all by carbon. So all carbons are sitting in the hexagon, and one layer of that layer is the graphene. So similar to the graphene, here in the boron nitride, boron and nitrogen are sitting in the hexagons, and those layer, they can sit on the layer by layer, and which is bonded by van der Waals force. But the hexagons are bonded by covalent bond, and its band gap is about 6 eV. So, and other properties are, it is highly thermal and chemical stability, and it can be also used as a neutron detector because it has high thermal neutron cross section. So here the band structure, here it has this one K, highest point of the valence band is in the K valley, and then the lowest of the conduction band is at the M valley. So when the electron is, because it is the indirect band gap, it has to involve some phonon. So the phonon in the hexagonal boron nitride is very active, that it doesn't lose much of energy as a heat, and then it still provides very strong emission around 215. And so that strong emission can be used for the UV emission. So it's not only UV emission, it can be because of the layer structure. This material is also attractive for the 2D, as a 2D material, because those layers are bonded by the van der Waals, and there are lots of research going on heterostructure with boron nitride, because the graphene and boron nitrides have very close lattice constant. Boron nitride could be the substrate for graphene, or there are lots of other material grown alternately or mixing of them. Those are called the heterostructure. And there is also some interest in the infrared nanophotonics, which is active in the infrared region. So recently, this another application is the single photon emitter. Wide bandgap materials are wide, forbidden gap is so wide that when there is some impurity or some defects and or even in the dislocations, its energy can be within the band gap. And those energies are, those impurity energy level or defect energy level, sometimes it could be donor, sometimes it could be acceptor, and sometimes it could be just the energy electron traps. And some of those defects could be also very highly localized state, and transition in those states can give the single photon emission. So I am going to discuss very close to that single photon emission, what we observe. And this is the material we investigated, we explore, and it's a single crystal boron nitride flakes. So the single crystal of the material growth of boron nitride is still in the very early stage, and we got small quantity of this boron nitride. It's not a big, it's very flake, like a very thin layer of the single crystal, and which is grown at Kansas State University. And they said it is, the method they use is the nickel chrome flux method. So we got very small quantity. This is not even very fragile. We have to take care very carefully. And another material we also explore was boron nitride powder, and purchased from a company. So SCM, this is the SCM image of the powder. It's a big flakes. It's a powder, so it's a crystalline quality. It's not very good, but still the emission for we studied some emission properties. And here are the TEM image of this boron nitride. So in the cross section, we can see clearly the layers, layer by layers, layer of boron nitride. And in some region we can also see some defects. Some layers are overlapped and some layers are missing. Those are, we call the dislocations. And on the top view, they are hexagonal structure, and we can measure the distance between one atom to another atom. This is from the high resolution TEM. All right, so for this material, we use photoluminescence spectroscopy to study the optical properties. And in our system, we have Ti sapphire laser. So Ti sapphire laser is pumped by solid state pumping laser, green laser, and then Ti sapphire laser gives the pulse laser. It's a pulse laser. Pulse width is about 100 femtosecond, and its repetition rate is 76 megahertz. So it's a stream of pulse, very short time, 100 femtosecond, and then another pulse is coming only after around 13 nanosecond. So that's the kind of laser system we are using, and the output of the laser is 780 nanometer. It's in the infrared. So for the photoluminescence system, let me go back here first. For the photoluminescent system, we have to excite the material by photon. So if you want to excite the electron from valence band to conduction band, the energy of the photon has to be higher than the band gap. So since our materials are very wide band gap, whose band gap is about 6 eV, so we should have the wavelength of the laser, excitation laser, around 200 nanometer. So 200 nanometer is far from 780. This is in infrared. So we have to convert that into 200 nanometer. So how do you do that? So we convert that using a third harmonic generator. We can convert into double the frequency or half the wavelength, right? And that's the second harmonic. And third harmonic is divided by 3, and the fourth harmonic is divided by 4. So these are the nonlinear process. So I will discuss a little bit later on. And we generate the laser. When it comes to the fourth harmonic generator, power goes very down. It goes down from 1 watt to 1 milliwatt, but that's still enough to study our material. So the laser light is incident on the material. Material is in the cryostat, meaning we can change the temperature from 10K to room temperature or even higher. And when we excite the material by laser of, let's say, 200 nanometer, it excites the electron in the material to the conduction band, and then those materials comes down, those electrons comes down to the valence band, right? Comes down to the valence band. So when the material, the electrons relax to the valence band, there are lots of different possibilities. It can recombine with the hole in the valence band. It can first transit to the donor level and then go back to the valence band, or it can go back to transit to the acceptor level and then go back to valence band, or may it go to donor first and then acceptor, emit the light, and then go back to valence band. And depends on how many levels inside, it can have lots of possibilities. So based on the emission its wavelength or energy and its intensity, we then explore what are the things going on in the this electronic band structure. So that's the way of investigating experimentally the material quality or material property using this photoluminescent system. So here we have Ti-sapphire laser in the picture, and third harmonic and fourth harmonic, and some cryostat here, and another is the monochromator. So once the light is re-emitted, right, it's called the luminescence from the material, we look at the light at different wavelength and measure the intensity. So that's why we need to separate the wavelength and measure at different wavelength, and that is done by monochromator. And inside the monochromator, it has a grating. So light, when incident on the grating, it diffracts and then it splits the light into different wavelength or color, and a detector is there to measure the intensity. So that's called the photoluminescent spectroscopy. All right, so in the this is a little bit detail about how we generate the third harmonic and fourth harmonic. So quickly, how it works is we pass the laser to the second harmonic generator. It's a crystal. It's the crystal, and it's a non-linear process. When we incident the very intense light on the crystal, in addition to its fundamental light, which is just passing through, it also generates some of the light, which is the second harmonic. Second harmonic means higher, double the frequency or half of the wavelength. And that light, after that, meaning it has a second harmonic and the third harmonic, sorry, fundamental. And to generate the third harmonic, those two light mix with the another crystal, non-linear crystal, to generate the third harmonic. But the problem is, when it generates the second harmonic, the pulse, light pulse of the fundamental and second harmonic, they do not travel at the same time. There is a little bit time difference. And to generate the third harmonic, both those pulses have to be arrive at the same time. So here is one trick. It uses the time plate. Time plate, it passes through the time plate, and then it will delay one of them. And once the time is at the same time, then when it strikes on the third harmonic crystal, it generates the third harmonic. And for the fourth harmonic, if we generate the second harmonic and then use that second harmonic light to the another second harmonic, that's the straightforward to generate the fourth harmonic. But the power is not that high when we generate the second harmonic and this another second harmonic, because this second harmonic is not enough to generate another second harmonic. So that technique doesn't give any light. So the another technique here is the mixing of the third and the fundamental. So it's a 3 + 1. It's not 2 + 2. So fundamental, we get a third harmonic here, and then we also have the fundamental, but the fundamental pulse is at different time, and the third harmonic pulse is at different time. And to generate the fourth harmonic, both pulse have to arrive at the same time. And the pulse width is so small, 100 femtosecond. So that's why we use here the delay line. It's just the light is traveling at some distance, and we can move that distance to adjust the pulse arriving time. And once those pulse arrive at the same time and we strike on the another higher harmonic generator crystal, then we get small amount of fourth harmonic. Okay. All right. I think I already discussed here. So here is the our result on the hexagonal boron nitride. So we have here first the upper one has lots of many emission peaks, and those emission peaks, once we get the spectrum and peaks, and each peaks are related to some energy level, and we have to explore that. So what we know so far is these peaks 5.78, 5.89, they are not from band to band, because it is not the direct band gap material. They are emitted with the help of phonon. Phonons are involved. So these are phonon assisted, optical and acoustic phonon assisted band is emission. And also there are other peaks 5.49. it seems like they are related to stacking fault, and then 5.31 is we assign it is related to oxygen in nitrogen. So but this is still in the debate, and we are exploring more. And another bottom one, in the higher range, the emissions are similar, just slightly intensities are different. And in the below this 5 eV, there is a feature, and which is not in the first sample. So the first sample is on anneal sample. This is exactly the sample we got from our collaborator. And then after that, we anneal it. Anneal means we heat up the sample at 900 degrees C for 1 hour. So idea was to improve the crystalline quality. And then what we got is a special kind of emission, and that has the sharp peak at 4.09 eV. And additionally, there are two other peaks, 3.89 and 3.69, and they are 0.2 eV difference. And that 0.2 eV is actually the phonon energy. Phonon energy in the boron nitride. So these are the phonon replica. So zero phonon line is the main peak is the 4.09. So after that, we try to figure out how to generate this emission line, and we explore, we anneal at different temperatures, keeping the same time, and most of the time we see that that sharp emission at 4.09 after anneal above the 700 degrees C. And we further try to figure out what's the optimized temperature and the time. So if we increase the time, right, or if we increase the temperature, if it is too high temperature, let's say 1000 C, it doesn't give that emission. And if it is low temperature, we have to anneal for the longer time. So optimized condition is like 800 to 900 degrees C for 1 hour in ambient air. Now, after that, we explore a little bit more about this emission. So what we did here is we measured the photoluminescence at different temperature of the sample. Temperature varied from 8K to 200K. And its intensity decrease, most of the time it happens in all materials because of thermal quenching. But the energy peak position remains same. And this another graph is for the different excitation power. We measure the photoluminescence at 8K, but we apply the different power of the laser light, or we change the intensity. So as we increase the intensity, it also increase the intensity of this emission peak. It's obvious, but the energy peak position remains same. So what does that mean? Is the energy peak position is robust, meaning it is not affected by temperature, it is not affected by higher excitation, and it is not related, meaning the material is not affecting its property, but the material is simply behaving as a host. So it is there is something normally it is because of the point defect. So there is a point defect inside the material, and that is hosted by boron nitride. And what we are seeing is from that defect, and those defects we call the highly localized, and the material is simply the host. So we also did a similar experiment for the boron nitride powder. And in the powder sample, we saw similar results. Peak positions are not very sharp, but nature are same. And also we saw similar sharp emission at 4.1 eV. The peak position is slightly different. And additionally, it also has few more peaks above that 4.1 and its phonon replicas. So the conditions are same. We also anneal the boron nitride sample, powder sample. Crystalline quality of the powder we cannot expect similar as in bulk. So, but the natures are same. And same in the excitation, power dependent and also temperature dependent. So anyway, this is the most important and summary of this photoluminescence result. So what we observe is from the boron nitride, we observe a line emission around 4.1 eV. Most people like to say it's 4.1 eV, but the precise number is 4.09. And if you look at the line width means the full width half maximum is very, very small, 0.2 nanometer for the bulk and 0.3 nanometer for the powder. And these kind of emissions are emitted, or we see that from the atomic spectrum. So that's why we are calling it atomic like emission. And because the line width is so small, this could be quantum emitter. And another one group has reported a similar result from boron nitride. And what was their result was they also observed 4.1 eV and its phonon replica, and whose shape and the peak positions are exactly same as we found in the photoluminescence. But how they observe is they scan the whole material and they found one spot, very small spot. See, the scale here is 200 nanometer. So it could be even less than 100 nanometer. So in one spot, they observe that emission. And they also they use the cathodoluminescence. In the cathodoluminescence, they use electron beam instead of laser. And they also observe the similar intensity of the emitted light. And they also measure one more measurement that's called the G2 measurement, and it's called the correlation coefficient. So that determines whether the emission is single photon or not. So single photon means it's just one photon, right? One quantum phenomena emitted light. So if we have one electron, only one electron recombined with hole and emitted the light, that's the one single photon. However, in our most of the light observation, it's not just one photon, it could be lots of. And this G2 measurement is the one which determines if it is a single photon or not. So how it is done is the light is splitted into two parts, and then those two splitted part detectors are put at the end of that. So if it is a single photon cannot be split. So that light will strike either on detector 1 or 2, right? Not both, because we cannot split the single photon. So by measuring the photon intensity on both with respect to time, and this measurement is done, and based on the quality of this graph, it is determined how pure the single photon characteristic it is. So we don't have this experimental setup, and we did not perform, so we cannot claim our emission is a single photon emission, but our emission is exactly same as there, and our emissions are very narrow. So the origin of our emission and the origin of the this reported should be same. That's why we are saying it is a atomic like emission. We cannot claim it's a single photon because in the photoluminescent system we excite the material with the laser beam, and laser beam diameter could be like a 1 millimeter, right? 1 millimeter, and this spot which is maybe 50 nanometer. So it's a very big area compared to that one spot, but still we got a similar result, meaning in our sample it's not only a few spots, those kind of spots are everywhere, and then all of them are emitting precisely at the same wavelength. That's why the line width is so small. So that's what we are claiming, and then we are saying it should be quantum emitter. And this single photon emitters are actually exploring further application in quantum information processing, which is called qubit. And in our general computer we use bits are 0 and 1, right? And what makes the 0s and 1? It could be anything. It could be yes or no, right? And there is a reflection or no reflection, and there is a electric signal or no signal, there is magnetic signal or no magnetic signal. There's two of them. But in the qubit, it has to have like a characteristic of our quantum stuff. It's just like in our quantum mechanics, when we have two states, it can also have a linear combination of those states, right? And it can have, it's not only zeros and one, it can have several eigenvalues. So those kind of processing is quantum computation, and for that, one of the candidate for qubit is the single photon emitter. All right, so next question is definitely what is that defect and which is emitting that sharp atomic like emission in UV range. There are lots of computational theoretical work, and they have predicted what could be the origin of that 4.1 EV. So most of the work done in the first principle calculation, and they have predicted that this should be related to carbon related defect, and those carbon related defect depends on where the carbon is sitting and how many carbons are sitting in the boron or nitrogen site. Its energy could be from 3.9 to 4.8 eV. So that's one theoretical calculation, and one calculation from first principle says it could be because of the two carbon sitting together, and that's called the carbon dimer, and that could be the origin of that 4.1 EV. And their calculation result is its energy is 4.3 eV. And some people predicted it could be different kind of structural combination. For example, it's a hexagon, but some places it is 5, some places it is 7, and still the average is 6. So that could be the origin, and that's called a Stonewall defect. And another report is if 6 carbons are sitting in a ring, as a ring in hexagon, and that also gives the energy close to 4.095 eV. So these are all theoretical calculation, but one similarity from all of them is it is definitely a carbon related defect, and what exactly is the defect, we need to have further more experimental evidence. And for that we did some investigation using X-ray photoelectron spectroscopy, XPS. So in the XPS what it does is it incident the X-ray and it emits the electron, and then the emitted electron is just like in the photoelectric effect. So by analyzing the energy of the emitted electron, we can measure the binding energy. Okay, so that energy, that binding energy gives the, what's the binding energy between boron and carbon, I mean boron and nitrogen, right? So if there is no other impurities, it is purely boron and nitrogen, right? Boron and nitrogen. So what is the electron binded to the boron and what is the energy binded to the nitrogen? So we should have these energy peaks from the XPS signal. But if the boron is also has some carbon or something else sitting nearby, if there are also some other element sitting nearby nitrogen, then we will get some small signal or small peak from the XPS above or below that main core binding energy. So what we did, we investigated those 2 samples which has 4.1 eV emission and which does not have 4.1 eV emission, and what's the difference in the XPS signal. So in the boron core binding energy, there is a small peak here, boron with oxygen. No, it is actually boron with nitrogen, and this emission is there. This is a mistake. It's nitrogen, and in addition to that, we also have the one additional peak. It appear in the sample which has 4.1 eV, which is boron binding, small signal from boron binding with carbon, which is not in the on-alien sample, which doesn't have 4.1 eV. And in the nitrogen binding energy case, it has the binding with nitrogen and carbon. This peak indicates that it is enhanced. So that means in the sample which has 4.1 eV, there are some carbon bonding with boron and there are more carbon bonding with nitrogen. So it indicates carbon is playing some role to generate the 4.1 eV. And we also did more experiment with another sample, right? So previous one is one sample was not anneal and one was anneal. So here both are anneal, but one is anneal very high temperature, and high temperature annealing also does not give any emission, 4.1 emission. So we also compare those two. So similarly here, it also has additional peak here, which is the bonding between carbon and boron,
Mim
which
sir,
is very
we have
clear
limited
and
time
pronounced.
now.
Okay, I don't need more than 5 minutes. It's
Okay, thank you.
almost done. And similarly, the enhanced bonding with nitrogen carbon. So our result indicates it is definitely carbon related defect, and as the theoretical study says, it could be carbon dimer or carbon ring, and more experiments are required. So we are planning to explore more in the TEM of these samples. Hopefully we can see those kind of structure, because in the TEM, high resolution TEM, we can see atom by atom, and we need to figure out how to distinguish it is carbon or nitrogen, right, or boron. So that's on the way. And another on the way is measurement of the lifetime of those emission light. So we are setting up a street camera, which was funded by National Science Foundation, and that's on the way. All right, so this is, I think I will skip here. And here is our final summary. So we explore hexagonal boron nitride, and we observe one sharp emission at 4.1 eV, which has very small line weight, and it is like an atomic emission, and it should have, or it could be used as a single photon emitter. All right, so I will stop here. And thank you for your attention. And here are some acknowledgement of my work. Most of the work is done by Nikesh. He recently graduated and working at Intel now, and my collaborators and people in the ESRC, where we do the XPS, and then funding agency. Okay, thank you very much.
Thank you, Mim Lal sir, for your very insightful talk. Now it's time for discussion. If anyone has questions, please raise your hand or directly ask to the speaker. Okay. Okay, if no question, then I have one. Could you show me your TM images, high resolution TM images? I want to know whether it is from powder sample or your
No, this is
crystal.
from crystal
Crystal.
bulk.
Oh. You told me that the crystal is very fragile, and so it is it is quite difficult to make a sample for TM.
No, TM to make the TM sample, we have to stick that even small quantity flake on another substrate.
Yeah.
It sticks on the substrate, and then we have to cut down
A very thin
lots
sample.
of stuff, lots of stuff for before we can measure the TM, because the size of the sample before we can put into the TM holder is like a 300 millimeter. No, 3 millimeter. 3 millimeter diameter, and the thickness has to be in a nanometer range.
Yeah. That's why I've asked you. The thickness should be very, very thin.
Very thin. It should be in a nanometer range. So the way we does is not that the whole material is 300 nanometer. So the sample is stick on the substrate. Now substrate is holding that, and then that sample is cut in a slanted way. It's cut by ion beam. ion beam, and then at the edge, it will be thin.
Okay,
So
okay,
only
that's a
that
great
edge
idea.
part is used to image the TM.
Okay, thank you, sir. Now, Leela ma'am, could you please ask yourself?
Thank you, Mim Lal sir, for your very nice presentation. It is very interesting. I would like to know something about you said that the sample preparation is a Ni chromium flux method, right? Is it a new method?
Yeah,
how does it?
I don't know that much because
Oh.
I
never
just,
heard about.
bought and got the sample from them. So, but little bit is,
Okay.
it is they use nickel, chromium, and then put some boron nitride, put in the crucible, and it is heated up very high temperature, like a 1500, 2000 degree, and then after that it's cooled down slowly. It's cooled down,
Okay.
and then it sticks some of the material which is stick this plate which is stick on the crucible.
So something like sputtering?
No, it's not sputtering. It's a single crystal growth.
Okay.
It's like a we melt the sample, right? And then we melt the
Heat it to
material.
high temperature and then
Yeah, very high temperature, maybe 2000 or maybe higher than that, and then slowly cools down. It crystallizes. It's not thin film technology.
It's a powder sample, you said
Yeah,
that.
it's a single
right?
crystal technique.
Okay.
Okay, any more questions? Is there any more question? Please put your question directly to the Mim Lal sir. If not, then you can contact later on with Mim Lal sir. We have his contact emails and everything stuff. So we are going to very late now. So I would like to request our president to close the session. Neelam ma'am.
Yes, okay. Thank you very much, Professor Mim Lal, for sharing your novel work and very in detail. That was very interesting. And thank you for accepting our invitation and giving the talk in the NPS series. So we are very much grateful to you. And thank you all the audience, even at night. So I have seen there were 58 audience participants were there. So it was basically very interesting talk. So with that note, I'd like to conclude the session 4 talk series of NPS for today's speakers. So giving him a big hand, please.
Okay, thank you very much for once again inviting me, and I missed meeting you when you came here, Neelam ma'am.
It's okay. It's okay. It's okay.
ल सबैलाई बाई है
Okay, recording
already
off गरे मैले